Okay, so as we start, we're gonna figure out an alternate method to figure out exact values of trig ratios for the angles 30, 60, and 90 and whatnot in every quadrant. And one way of doing that without having to adjust the special triangle and think about whether things are positive or negative is just to use those special triangles to basically make a big magical circle, which we can then simply just apply. So I've started this fairly simply by putting in the coordinates of these different points if we define a circle on the Cartesian plane with the origin as the middle and with the edge of the triangle at 1, 0, or sorry, the edge of the arc, with the top of the arc at 0, 1. So basically this is what would be a line with a radius of 1, or we could say with an angle of 0 degrees. This would be up at 90 degrees, where you have, a rise of 1 for a run of 0. And then all of our 30, 45, and 60 are on this arc between there, right? So we're making a circle and thinking, okay, 30-degree angle, 45-degree angle, and 60-degree angle. So now, using these special triangles that we generated yesterday, I started filling in the blanks. We said that, of course, just by definition, at 0, this is the point 1, 0. At 90 degrees, this is the point 0, 1. But in between there, we know that the 30-degree special triangle has an x value of √3/2 and a y value of 1/2. We know that a 60-degree triangle is the same thing, just flipped. And somebody pointed out, we don't really need to know the 60-degree triangle as long as we know the 30-degree triangle well, because it's just the same thing reversed. And then the 45-degree triangle, well, what will be these points? What's the x value here? How far is this measurement here? I see it's bigger than half. How big is that? Maybe √2/2. And on that same triangle, if the x value is √2/2, what's the y value? √2/2. And some of you were looking at saying, this isn't quite the triangle I remember generating. The one that I generated for 45 was 1, 1, √2. This is the one where we had taken the hypotenuse and made it into 1. So to generate the unit circle, we're going to use these special triangles where the hypotenuse is 1. So we can be talking about, the radius of the circle always being 1. Okay? So that's the first quadrant of this unit circle. So this line segment here, the top one is 1/2. The next one is √2/2. And then this last one here is √3/2. Sorry, yeah, having your off your map. Sorry, you're looking at this great. And how do the coordinates of these points relate with the rotation angles? How is that relationship? What's the deal with the points and the coordinates? How would you find the coordinates from the angles, or how would you find the angles from the coordinates? For example, how is this √3/2 and 1/2 related to the fact that that's at 30 degrees? What's the relationship of √3/2 and 30 degrees? How could you find √3/2 with 30 degrees? Or how could you find 30 degrees from √3/2? What's that relationship all about? Yeah, that's the cos relationship. Nice, yeah. So the x value, the adjacent to the angle, ends up being the cos, because it's like, we've set this up so the hypotenuse is always 1 in this case. So x value ends up being what the cos of the angle would be. The y value, how would you find that from the angle? Let's think about 30 again. How's 1/2 related to 30 degrees? Yeah, that's the sine value. That's the sine of the angle. So in this case, we're using not just random numbers. We're choosing to make this circle based on the ratios we found yesterday, based on these triangles. Basically putting these triangles on this circle and saying, here's where these points would be in these different quadrants. So, if we take that and we move it around, if we take that same triangle and we flip it, and we say, okay, what about 30 degrees in quadrant 2? Well, then the x value is negative, but the y value is still positive. What about if we take 45 degrees and put it in quadrant 2, 135 degrees? Well, then the x value is negative, but the y value is still positive. And you can do this with all of the quadrants. Take the same reference angle, move it to whatever the rotation angle is, and then use the different coordinates from these points. By the way, you have a unit circle here. It may be worth filling in, so you have that tool for yourself. This circle above is called the unit circle. I'll give you a moment just to fill this in. I recognize lots of you will like to have this. Well, I guess you have it in your book, so I don't need to leave my screen there. You have the circle right there. So in this unit circle, if r is 1 is by definition, then sine of theta ends up being y, cos of theta ends up being x, for whatever the point you're at is. And then tan is always sine of theta over cos of theta, by definition, so y over x. So that means this ends up being pretty useful with unit circle. You kind of apply this to a bunch of different situations to find an angle you're looking for, or to find a point you're looking for, find a sine or cos, like that. So let's use the unit circle to find the exact value of the trig ratios for a rotation angle of 240. Did anyone speed run? Alright, do you mind if I just show this here?
Yeah.
So Mario's written out his numbers on here. Now, we're asked to use this to find the exact value of the trig ratio at 240. Okay, 240 is here. Now, some of you guys are already thinking, okay, that's the 60-degree special triangle in quadrant 3, right? It's down in the bottom where it's negative and negative. And I look at this, I see, okay, at 240 degrees, I see my coordinates are negative 1/2 and negative root 3 over 2. So let's just try to remember here. So with the unit circle, what was the sine again? How was the sine of that angle related to these coordinates?
No, sine was y.
Sine was the y value, okay. So in this case, at 240, the value should be root 3 over 2. What's the cos? Yeah.
Negative 1 upon 2.
Cool, sounds good. And then how about the tan? Remember the tan we don't have directly on here, but how do we find it from this?
Oh, like multiply or something?
Sine over cos? Sine over cos, or you can just think about that as opposite over adjacent, or y over x. So we have negative root 3 over 2 over 1 over 2. Uh-oh.
Negative.
Oh yeah, so it ends up being, oh yeah. So what's that end up being?
Root 2.
Positive or negative? Negative over negative? Good. Or tan in quadrant 3. Right, you don't even really have to think about the signs as soon as you know we're talking about tan in quadrant 3. Oh yeah, tan in quadrant 3, that's always positive. Okay, so we still can remember those cast rules. Okay, now look at this next one. You use the unit circle to find the exact value of cos under 35 degrees. Why don't I draw this up here if you guys are doing like this? Can you guys try these? See if you're able to do A, B, C, and D from what you have here. While it takes me about 36 minutes to draw this unit circle for you. So let's start trying to use class example number 5 questions, see if we can move. Ready? Okay, so first of all, I'm looking, okay, at 135, I have negative root 2 over 2 and root 2 over 2. With cos, am I using the x or the y value here?
X.
X value. So, negative root 2 over 2. Yes? Cool. Okay, how about tan 120? Tan 120.
It should go some or something of
So how's tan related to our sine and cos again?
tan.
It's maybe
Oh, yeah,
helpful
this
to
one
keep in
makes
mind tan of whatever
Cos of something
is equal to sine
Sine
and cos. Cool. Or y over x. Right? So if I have tan of 120, continue with my 120, so I have negative, and I end up with 3 over 2 over 1 over 2. Sine of 180, oh, this is an interesting one. I'm guessing you guys have already gone through and filled in all of these unlike me though. So sine, is that the x or y?
So 1, 0.
Yeah, so at that point, 0. And how about tan of 270?
Non-different.
Tan of 270. Well, let's think how you get there. So what's the y value at 270?
Negative
1. What's the x value?
0. Non.
Great. If you write, by the way, something over 0, I understand that you're saying it's undefined. Right? At this point, I recognize that when you're saying something is about the 0, what you're trying to communicate is this is an undefined expression. Okay? So that's fine. How about this next one? A and B are 2 points on the unit circle. If it rotates from A to B, and recognize counterclockwise, pretty important thing here to see. If it goes counterclockwise from A to B, what angle is it rotated? So first of all, what point is A at? On the unit circle, what point is A at?
135,
Yeah, so this is 135 degrees, nice. And what point is B at?
240,
Man, this person talking about 95 sounds kind of realistic. Eh? So then how do I find the rotation? Thinking about this, so going from here to here, counterclockwise is this way. Grasp the difference? How far has it moved from one to the other? Cool. So if it's asking how far it's moved and saying from one to the other, what's the difference between the two? So I just subtract them. How about this? This is a bit of a, okay, how is the unit circle set up? So we're trying to find some point on the unit circle. We don't need an exact value here, decimal is fine. But we want to know on this unit circle, some point that is over here, 148 degrees. So what do I know, what do I know this will be kind of close to? What's it going to be between?
probably 135 and 150.
Okay, so it should be between the 145 and 150 points. It's going to be close to 150, but not exactly that. How would I find the x coordinate there? Let's think about how the x and y coordinates were found in them. So this will be some point called, let's say, xy. So how is the x coordinate related to the angle again?
We can use take the angle from 180 and then do radius and then I guess
Let's go even simpler. You are on a track we can do. Let's go even simpler. Let's go back up a step. When we were here, We were on question 6. Or sorry, on question 5. How are we finding the cos of 135, for example? What were we looking at in the unit circle? We were looking at the x-coordinate, right? And how are we finding sine? Well, we were looking at the y-coordinate. So let's think about this angle then, using that. So at 148 degrees, we want to find these coordinates. How can I find the x-coordinates? Well, couldn't I just go, this is the cos of whatever the angle is? And how would I find the y-coordinate? Well, wouldn't I say that's the sine of whatever that angle is? And the nice thing is here, my sine is just going to tell me what I should already know. In terms of something being quadrant 2, what do I know about the sine of the x value? Quadrant 2. Negative. What do I know about the y value? Okay, so let's check that. Let's see if your calculator's agreeing with you. Cos of 148. That look about right? Come here. Look about right?
No, it's negative. Oh, yeah.
And what about the sine at 148? Does that look about right?
Yeah. I thought I'd say something.
That cool? So how do I find the coordinate? Well, I just put in for the x value the cos, for the y value the sine. This is just based on how we set up the unit circle. So we could say this is at point negative 0.8480, comma 0.5299. That's the point that is on the unit circle here. Now what about this? What about this? Going backwards. This point is on the unit circle. So now, instead of having, what we had last time was here's this angle, find the point. Now what about if we have this point, what's the angle? Okay, how can I find that? How can I find whatever the angle is on this unit circle? That second line is just saying on the unit circle. Well, what's the x-coordinate going to correspond to? Yeah, cos of the angle. What's the y going to correspond to? And let's think about this. Point, negative x, positive y, what quadrant are we in? Quadrant 2, awesome. Okay, so I'm looking for cos of theta is negative 0.8829. So I check cos. It looks to me like theta is 152. I see blank stares and wondering, does this seem reasonable?
Yep.
Yeah. I also see some swearing under your breath. Maybe is that the range of outcomes right now?
You just shifted the cos to the left side and you're trying to find it out.
Yeah, right, inverse cos, of course. If you're looking for an angle, you're always using the inverse, yeah. Now, how can I check if I'm right here?
Or do that.
Yeah, why don't we do the sine? Let's see if the sine ends up being the same. Is the sine 0.4694 at 150 degrees? Actually 0.4695 on this table, but yeah. Sine theta 0.4695 and theta is also 152. So the angle. And I actually, a trig table is fairly useful in a case like this. Yeah, but if you didn't have a calculator, this would be happy. This is what my mom used in school. The only option I had. So like when I look at this and I look on the degrees, 152, what does it say for sine? What does it say for cos? Does that match with what's here? Oh yeah, it's the same numbers that are on there, right? So looking at a trig table, it's kind of like, oh, I this is more easy. Yeah, and so in some cases this is kind of nice. And actually, I talk about these often. I recognize you have calculators, most of you use them. But I really do kind of like this because like you can just methodically see from 0 to 90 how sine changes. From 0 to 90 how cosine changes, and then what happens to the positive, negative, that kind of stuff. So if you want one of these, I have some. I don't have enough for all class, but I can print stuff. If trig tables are helpful for you, I'm perfectly happy to use it there. They're certainly allowed.
What is this one then?
Oh yeah, but so those of you who are wondering, like, hey, Boyce doesn't seem to have a calculator. What's he doing? I'm just looking at this. That's not fine. You're thinking I was super quick here. No, I'm just reading.
Mr. Boyce,
Yeah.
I just got, like, I typed the sign value and I got 28.
Oh, yeah. Very good, very good. So let's think about something. That's absolutely right. You're totally right. So if you put that in your calculator, it says sine is 28 or whatever. Now remember, when you put sine of something in your calculator, it's always going to tell you the reference angle. It's always going to tell you kind of the simplest angle you can find. So where is sine positive? It's in quadrant 1, they all are. It's also in quadrant 2, not in 3, not in 4. So let's say we're looking for some point in quadrant 2 here. The y value, the one you initially find, is actually going to be what you're like when you use cosine, because this is like the first negative value you run into. Cos is positive here, cos is negative here. But when you're finding a sine value, let's say you put sine of 0.6 whatever, it's going to give you some value in quadrant 2. And then you recognize, wait, the point I'm looking at is in quadrant 3. This is where that kind of special triangle work was fairly important to think about. Is, oh, this is a point in quadrant 2. So what's the relative angle in quadrant 2 that is related to that reference angle? The reference angle of 28 degrees corresponds to this point of 152 here. Right, because this angle of 152 degrees tells us that angle of 28 degrees. Yes, there.
So in the last question we just did for sine, we supposed to do what is it, second sine, or just like?
Oh, right, yeah. Yes, anytime you're using a trig ratio, like if you're looking for an angle, use second sine or second cos. But also, let's just think, we have cosine of an angle equals this. We're looking for the angle. When we're trying to sort of do algebra, what do you try to do to try to find? You try to isolate the variable. How can I isolate a variable from a trig ratio? Probably the inverse trig ratio. Right, so like to get theta by itself, do the opposite operation of cosine, which is inverse cos. Yeah. If you want a rule of thumb, if you have the point, use the inverse cosine or inverse trig ratio. If you're looking for the point but you have the angle, use the normal trig ratio.
So Mr. Boyce, for the sine thing, like, are you just taking, like, are you doing the opposite, like switch into 180 minus 28 here thing? Like, is that what you're doing? Because
Yes.
Okay.
Yeah, you're saying in quadrant 2, which I already know it's in. In quadrant 2, which I already know it's in, what's the sine of theta thing? Well, it's 28 degrees in quadrant 2, which happens to be 152 degrees as a relation. So it is always important still to keep in mind that your calculator is mostly going to talk about reference angles, and then it's your job to switch that into your rotation.
So you just have to see what's up.
Exactly.
Okay.
But there are often tips, like in this case, the fact that it's negative. Oh yeah, in quadrant 2.
Yeah.
Or the fact that cosine of theta was using this negative number. Oh yeah, in quadrant 2. But if you only had this, if you only had that it was like x is this, y is either positive or negative, then you're like, oh, then it's 2 or 3. But that's not. Okay. So now, using either special triangle, which I love, or the unit circle, which you have in front of you, we're going to try to find the exact value of cos 300 plus sine 330. Now, actually, why don't you guys start doing this, and I'm going to do this using special triangles. Let's see if we get the same spot, okay? This is the secret where you learn Mr. Boyce can barely use a unit circle. It's pretty simple, just look at it. So remembering on a unit circle, looking for cos of 300, you go to 300, and you find the x value. Looking for sine of 330, you go to 330, and you find the 1.
And then you just have them together?
Then you just have them together.
Okay. Cool. Yeah.
Yeah. Yeah. Which ones? I'm gonna do them. Oh, but you're wondering, all this means is sine of 225 times sine of 225 plus cos of 225 times cos 225. When you have that squared, it means the whole thing squared. How they look? We agree, we disagree? No one hates me yet for this? Great, thanks. I appreciate you all too. This is nice, I've sprawled B out to take over all of C. So I'm going to do what I was doing yesterday. I'm going to rewrite these as using the reference angle and just thinking about plus or minus with the angles. You can keep going using circles, you'll know the numbers. But sorry, going back to my special triangles. Going back to my roots. Tan squared.
No, for the other one, it's 2 times.
Oh yeah, true, yeah. I was thinking for B.
That is definitely not where I took that.
So do you see what I did? This is still me going with special triangles. So I thought, okay, I know that 225 for both sine and cos. Quadrant 3 is negative for both sine and cos. So I thought, okay, I'm talking about negative sine of 45, negative sine of 45, negative cos of 45, negative cos of 45. I thought the special triangle in quadrant 3 is a negative and negative. You guys may have checked that and saw sine of 225 is negative root 2 over 2. And you have that times itself. Plus cosine of 225 is negative root 2 over 2 times itself. So you end up with 2 over 4 times 2 over 4. Uh-oh, I'm wrong. 2 over 4 times 2 over 4 is 1 over 4.
But your square, no, because you have 2 times 2 in the square root, so then you're square rooting, like...
Yeah, so you end up with root 2 over times root 2 is 2. Yeah, negative times negative is positive. Oh, you guys not want to see the back, sorry, for butting in. But so we end up with 1/4 plus 1/4, so 1/2.
Where are you getting the 1 now?
Sorry, it's 2/4 times 2/4. Yeah, so 4/16, which simplifies to 1/4.
Oh my...
Yeah. C?
Yeah.
I'll do C.
No. There's like B. I'm getting this wrong, right? I think it should be this. I did this, and then after that, so 1/2.
Oh, so you're squaring the whole thing. Okay, so that's 2.
Yes. 2 1/4, and this is 1/4. I just got this, but 1/2, 1/2. And 1/2 squares.
Yeah, you're right. Sorry, I squared it again after. I don't know why I just redid my work. You guys are right. This stage phenomenon is a bad one, guys. Yeah, go back to what I said before. Half plus half. Sorry. My notebook's not working right now, so let's talk through C. Maybe I'll actually write it up here. This is probably one that we could use some paper for, anyways. Why don't I see if I can end this? why don't we just try to see here? So 2 times tan 1. It's all working exactly according to plan here. Just how we intended this. Okay, great. So 2 times tan 150. Let's deal with that first. As our wonderful program comes back up. Oh great, now we're getting interrupted by a phone call. Okay, I will go over this with you. I'm going to answer this call. You can feel free to start working on the homework. You can see where we're going. But I will go over this with you just a second. Hello. She's not here. Nope. Okay, sorry, I hear there's some controversy going on. What's the issue we're figuring out? Should we just look and see?
Yeah.
All right, 2 tan 150. First of all, I'm in quadrant 2. I'm talking about tan, so this is going to be a negative value. So we're talking about 2 times negative tan of 30. When I'm thinking about using special triangles, you can just look at 150 and find the tan by going y divided by x. And that's 5. And then I'm going 1 minus tan of 150, or negative tan of 30 times negative tan of 30. That's why I'm rewriting this. Sorry, as I go back here, this was 1 is 1/2 plus 1/2. So I'll just fix that now. So this first one, 2 times negative tan of 30. So I'm looking here, say tan 1/2 over root 3 over 2. 2 times negative 1/2 over root 3 over 2. So that's a nice and lovely fraction to work with. But it ends up just being 1 over root 3 over root 3 over 3. And this bottom ends up being 1 minus exactly this times itself. Root 3 over 3 negative times negative root 3 over 3. So when I rewrite all of this, so I have 2 times negative root 3 over 3. And recognize the way I'm converting this disgusting thing into this is I'm simplifying this fraction to 1 over root 3 and then rationalizing the denominator. And then the same thing on the bottom here. So over 1 minus, okay, negative root 3 times negative root 3. 1 over 3. And then 3 times 3, 9. Okay.
1 over 3.
Yeah, exactly. So I end up with 1 minus 1/3 on the bottom. So then when I finally rewrite this one more time, I end up with negative 2 root 3 over 3. That's my numerator. Over 2/3. That's my denominator, right? 1 minus 1/3 is 2/3. And can I simplify that a little bit further?
Yes.
Yeah, right. I can still do my, a times b and b times c thing with fraction to end up with, let's see, negative 6 root 3 over 6. Oh, any more simplifying I can do? Oh yeah, so this ends up being negative root 3.
Yeah, I got it.
Now, this is a case where I think if you did this with the unit circle, which is part of why I gave you a bit of time here, I bet you found that easier than I did.
No, I did the geometry that was easy.
Okay. Mine's, I don't think this is very hard math, but it's a lot of steps. It's a lot of just following through, okay, how do I simplify this next? How do I simplify this next? The reality is, you already have the answer at this point here. That just needs a lot of simplifying. That's not a very usable answer. That is a number, right? It's just if you could say that, oh yeah, this is the value, I'm going to say, good joke. you need to simplify that. But right, this is all of the like trig work has been done. Now we're just working with simplifying the gross expression. So anyways, it ends up being negative root of 3. Yesterday you guys did questions 1 to 5, am I right? So today you get to continue on. I'm going to be doing lots of these as you go. I'll let you guys get to work. You can work through the whole section. But yeah, you can be doing these on your own. And then as we're going, if you want to use MathLab, that's fine. But in here, I'm going to be working on some of these questions with those who want. Okay?